Get it over with.
Let's split this out.
Yep. Yeah. So section 5, I didn't split into 2 parts. So, I mean, there's kind of quite a bit of notes, but like they're not technically too difficult. We should know how to simplify a square root, so it should be review. Technically. So yeah, can anybody tell me what a square root is or a radical?
A number that is the product of two of the same numbers.
Okay.
Like 8 times 8, 9 times 9.
Yeah, so basically square root, I could have a square root of 64,
Not the
which
8
is
times 8.
8. Yeah. So we've done square roots. They're the opposite of like perfect squares. We've been working on perfect squares, so nothing crazy there. So the radical is basically just like the symbol used. So this is the radical symbol. We're always going to use square root in this section. With next chapters where it gets fun, so then we could have the cube root or the fourth root or fifth root or whatever. Okay. So technically, a square root, we're automatically assuming that there's like this imaginary 2 with a radical symbol, because I could have a 3 there, makes it cube root. We could have a 4th root, and all things. But if there's no number with the square root symbol, we're just assuming it's the square root of that number. Okay? So we're working with these kinds of symbols, and we're going to get solutions with these kinds of symbols. So remember, we're still trying to solve quadratics. We're going to work with square roots before we actually get to a quadratic that could have a possible answer like this. That's where we're going. So we have 2 properties that we're going to use today. We have the product property. Technically, it means if I have the square root of a times b underneath the radical sign, I could break it to be square root of a times square root of b. And I could go vice versa. If I have 2 radicals multiplied together, I could join them into 1 radical. We will use that quite often. We also have a quotient property, which is the exact same thing, except it's dividing. If I'm dividing a and b, I could break the radical. So it's 2 different parts, or I could put them together and make it 1 radical. Doesn't matter. Okay. I would like to simplify the square root of 75. So you gotta dig back in your brains how we simplified a radical sign. Does anybody remember how to simplify the square root?
Nope.
Nah.
Not on the top.
Okay. So yeah, if it was a perfect square, we could just say the number. This one isn't a perfect square. But the goal is basically to figure out what perfect square divides into this number. So is there a perfect square that divides into 75?
No. Well, probably is.
There probably is. So a perfect square is something like 4, 16, or 4, 9, 16, 25, 36, 49. Do any of those divide into 75?
What were those called up above the
Product property and quotient property? Yeah, that's the goal. But you guys have to figure out what perfect square. 75 divided by 9. Yeah. 8 1/2 is a perfect square. So 75 divided by 4. Let's just start with the first perfect square. Does that divide evenly? No. What about 75 divided by 9? I already told you one. No. 75 divided by 16. No. 75 divided by 25.
Yes.
Yay! Okay. So I can rewrite the square root of 75 as 25 times 3. Right? Everybody would agree 25 times 3 is 75. Okay? So then here's where I use the product property. I want to split it into two radicals. Have the square root of 25 times the square root of 3. The main reason why I want to do this is I can simplify the square root of 25. So the square root of 25 is 5, and then I multiply by the square root of 3.
Oh, this stuff. Okay. I was really, really bad at this for some reason.
Well, hopefully you get better at it.
Because now it's just, I look at it and I'm like, oh, it's super easy.
Yeah. Okay, so 5 times square root of 3 is the same thing as the square root of 75. You could type them both in your calculator. They would give you the exact same decimal approximation. Okay, let's do another one. We have the square root of 7 times the square root of 35. I would like to simplify this.
You can make 35 into square root 7 times 5.
Okay. So I can have square root of 7, then 35 instead of 7 times 5. Yeah. So looking at it, 7, 7, and 5, none of those are perfect squares. So I can't simplify any of them. But it would be nice if I could combine the two 7s together. Because 7 times 7 is 49. 49 is a perfect square. So I could basically just move my radicals around and do 7 times 7 and then 5 by itself. That's a legal thing I could do. So I have the square root of 49 times the square root of 5. And the square root of 49 is 7. Simplify. You could have done that one a lot of different ways. You could have multiplied 7 and 35 together to get whatever number that is, a large number. Then you could have just tried testing dividing by perfect squares until you get the right one. So you get 49 basically. All sorts of ways. Here's this lovely thing. Square root of 100 over 169. So now we're kind of moving into the quotient property. No. So instead of one radical, I could write it as two separate radicals. Yeah? What is the square root of 100? 10. The square root of 169? Yep.
I'm
13. Yeah. Technically, the state standards say you're supposed to know all the perfect squares up to 20. So like 14 squared, 15 squared, 16 squared.
I was actually.
Yeah. Most people know up to 12. Those are the ones that we use most often anyways. Not too shabby. Okay, let's do the same idea.
Two separate
Radicals.
Can't do anything with 11, but 12.
Yeah, so 11 stays underneath the radical sign. Square root of 144 is 12. So then, that's simplified.
I like this problem better than the last
What?
one. I like this problem better.
Oh, you won't in a second.
Don't say that.
Don't rationalize the
Rationalize the denominator. This is where the quotient property probably won't win.
That's two big words.
Yeah, because our denominators have been perfect squares, but then the situation is what happens if my denominator is not a perfect square. So I can have a square root in the denominator. Technically, that's unsimplified. So we have this process called rationalizing the denominator to move the radical out of the denominator, basically. So I'm going to say process of multiplying to move the radical out of the denominator. So, for example, if I had like 2 over the square root of 3. Square root of 3, we know it's not a perfect square. But I can't just leave it like this is unsimplified. So, I would like to multiply by something over off to the side to get square root of 3 out. So, basically, I'm going to multiply by what's in the denominator. So that way when I do square root of 3 times square root of 3, I multiply to create a perfect square, basically. But if I do it to the bottom, I have to do it to the top. So this part I like created myself, and then I will multiply straight across. We have done this before, sometime in math. Right, we only multiply like terms, square root of 3 and square root of 3 is 9. And then we should know square root of 3. Of course, square root of 9 is 3.
It's not that bad.
No.
Correct, only at least. It's just, it's my bad.
You know, so long. Yeah. So that process, it's not too tricky. You just have to remember that that's what you do. Conjugates is slightly more complicated. So basically a conjugate is if you have the sum of a binomial. Does anybody remember what a binomial is?
It's got 2 things.
2 terms, so like x plus 2, for example. Maybe that's our binomial. The sum of a binomial changes to a difference, and vice versa. So conjugate, the conjugate of x plus 2 would be x minus 2. You just kind of change the sign. We're going to be working with radicals, so if it was 1 plus square root of 3, conjugate would be 1 minus square root of 3. So, our example, we could have 2 over 1 minus square root of 2. So then this is different because I have 2 terms in the denominator instead of just my radical sign. I still want to like rationalize the denominator and do all the stuff. But I have to multiply by the conjugate. And so the conjugate of 1 minus square root of 2 is 1 plus square root of 2. We'll have to do that to the top since we did it to the bottom. Fun times. So we're going to be good at multiplying. Dylan's so excited. He just can't even contain himself. We're going to do an example of each. Because it's so awesome. Yes! Okay. So I guess the first thing I would do, if you have the square root of 2 over square root of 15, I would still use the quotient property and break it into 2 radicals. Just in case there's one that could be simplified. In our case, neither of them can. None of them are perfect squares. So since I know I can't simplify the square root of 15, I should multiply by what? Yeah. So multiply by square root of 15. On the bottom, if I do it to the bottom, I have to do it to the top. It's kind of like the equation, if you do it to the right side, you have to do it to the left side. Multiplying straight across, what is the square root of 2 times the square root of 15?
Square root of 3.
Woo. And the square root of 15 times the square root of 15?
2.
Yep. Feels like I don't know. What's the square root of 225?
15.
15! So it goes back without a radical. Wow! So magical.
Magical is not
Simplified.
the word I would use to describe this.
I think it's magical. Okay, here is this guy. Here's the best one. 4 over 5 minus the square root of 2. So I have a binomial in the denominator. What am I going to have to multiply by?
Space. Can't you keep 4 is a perfect square?
But there's no radical sign on it.
Is doing my invalid.
Yeah, well,
Well, I have no one for science. Is that what?
That's what Dylan's focused on.
You say science, that's good.
Eighth
Okay.
period.
How do you take that next? My science.
So I'm still wanting to get the square root of 2 out of the denominator, right?
yes.
So I need to multiply by something.
Square root of 2.
Okay?
Top and on top.
But since it's a binomial, I need something a little extra with this.
Plus 1. Alright.
We have a plus sign. But it's a 5. Because I'm taking this 5 minus the square root of 2, I'm just multiplying by its conjugate, that lovely word. So I changed it from a difference to a sum.
So you're trying to cancel that out.
Yes. Yep. We're trying to cancel out 5 minus square root of 2. So I need to multiply straight across. But notice I have binomials, so I'm going to be off to the side. I multiply what is 4 times 5 plus square root of 2 by distributing.
20. Square root of 8.
Ooh, 4 and square root of 2 are not like terms. So that's right, that's 4
square root of 2.
Okay, so that's my numerator. I have to do the same thing to the denominator. Go off to the side, rewrite it. And we need to distribute this lovely thing. Positive 25. Yeah. The next part.
5. Square root of 2. 5 square root of 2. Square root of 20.
Okay, so we do the conjugate because this radical cancels in the middle. Plus 5 square root of 2 minus 5 square root of 2. Square root of 4 simplifies down to 2. So 25 minus 2, which is 23, and that's my denominator. So I magically got the square root symbol out of the denominator. Woo! Nice, right? Okay, so now that we've worked with radical signs, we can move back into quadratic equations and solving them. Yay. So we have 2 more examples. Okay, so these ones I actually really like because you don't need to factor it because I don't have an x term. So in this case, I only have x squared, so I could solve it for x squared. And that's what we're going to do. So if you had an x squared term and an x term, you'd have to factor it. And we were pros at factoring last week. Now this is a different way of solving. Okay, so I'm going to get this guy by itself. What would I do first?
Add 15.
Okay,
Both sides.
you're trying to treat it like a linear thing. So I have 2x squared equals what? We're adding
Oh, we're adding. 80.
80. Trying to get x squared by itself, so we're going to 2 over dividing. So x squared equals
40.
40. How do I get rid of the square root?
Square root it.
Square root it. So the tricky thing with square roots, because it's to the second power, I should have 2 solutions. So my 2 solutions come from the positive and negative square root sign of 40. So every quadratic, you should 90% of the time get 2 answers. In our case, they come from I'm not done yet because now we know how to simplify the square root of 40, and we should. So what perfect square divides into 40?
I know that 4 and 10 do.
4 and 10, so I could rewrite 40 as 4 times 10. And then I could do the product property and split the radical. That's square root of 4 times square root of 10. And then we know the square root of 4 is 2. Square root of 10. There's my lovely answer.
Don't forget that plus or minus.
Don't forget the plus or minus sign. Yeah. Nice, right?
Yes.
Yeah. Instead of a whole number answer or a rational number or fractions of decimals, you get square root answers. Okay.
It's not that.
It isn't. Okay, so same thing. I don't want to square this out or anything. I just want to isolate that parentheses to the second power. So that way we can square root the sides. So let's move 1/3 over. And how would I do that? Nope.
Divide.
Okay, instead of divided by a fraction, I'm going to do
Divide by the reciprocal.
multiply by the reciprocal. It's nothing. Right? Because 3's cancels, 1's canceled. And x minus 4 to the second power equals 33. So now I have this whole quantity to the second power by itself. We can square root both sides. Right? So left side square root and square cancel. I just have x minus 4 on the right side. Got that lovely plus or minus sign with the square root of 33. Is there a perfect square that goes into 33? No. Because 3 and 11 go into 33. Those are the only two numbers that go into 33. Neither of them are perfect squares. So this is going to stay as is. The x isn't isolated by itself yet. So we're going to add 4 over. And then 4 and square root of 3 are not like terms. So I'm just going to write as 4 plus or minus square root of 33. Yeah. So we can get answers like that. Thanks.
Oh, there's more.
Oh man, we couldn't just end without a story problem. So, sad face. Yeah. So we're modeling dropped objects. So basically, if I'm on top of a building, then I'm just going to check my phone up to make sure it doesn't crack or anything. This is a dropped object model. Okay, so this looks like h equals negative 16t squared plus, I'm going to say they say use h naught, they might use s. Technically, it doesn't matter. H naught is initial height. Then I'm using that 0 as a subscript because that's at time 0. So at the height at which I throw my phone off the ledge or drop it. Okay? And then h is just height at time t. Negative 16 is always there because that's like the force of gravity on the object. We're going to use this later. We're going to modify it to include velocity. So you should just start learning this because it'll make it easier later on. Okay. So if you drop an object off the roof of an apartment building that is 240 feet tall, about how long will it take the object to hit the ground? Yep.
So your initial height is 240.
Right. So h naught is 240. That's the height at which I toss it off. So my equation is negative h equals negative 16t squared plus 240. Okay. I'm gonna ask how long it will take, so I want to solve for t, but what height is it gonna be at when it hits the ground? 0. So my h value is gonna be 0. So then I need to solve this equation.
Subtract.
Okay. Anybody know what that is? Me neither. Maybe 15. That's my guess.
15.
Oh,
Square root of 15.
75 plus or minus. Okay, if I'm working with time, I'd actually like square root this out. So what is the square root of 15? Maybe I gotta type that in the calculator. Square root of 15. Close to square root of 16, so it's almost 4. So maybe like 3.9 or 3.
3.87. So
Okay. And then with plus or minus, technically our time we can't negative time. So it's just 3.87 seconds. That's all it'll take to hit ground. Nice. See? So much fun. I'm so happy we did that today.
I'm so tired.
Okay. Okay, bye. We have a test on Wednesday and Thursday this week. Get excited.
I do learn so much this weekend, and then we have practice this morning.
Yeah. Good morning practice because of the junior hiking. Fun times.